In this video, we are going to once again be looking at integration by parts, but now we're going to be looking at repeated use of integration by parts. Yes, as much fun as it is to do once, we sometimes have to do it 2, even 3 times in one problem. So let's get started. We're starting with the function x squared e to the x. So we have an algebraic function and we have an exponential function. So if we just write L-I-A-T-E here, just as to remember, the algebraic function is here, exponential is here, so this becomes my u and my dv. So over here, I have identified u as being x squared. The derivative of that is 2x. dv then is e to the x, and forgive me, I forgot to put the dx on there. Ex dx. The antiderivative of that is e to the x. All right, so then this part right here goes with this. So we put that into the formula. We have x squared times e to the x minus the integral of e to the x times 2x dx. We can bring the 2 out in front. And so then we're left with the integral of x times e to the x dx. But we have a problem here. We still don't know how to integrate that. That's an integration by parts problem. So when you go through and you do integration by parts, and this integral that we have over here still cannot be integrated, then we have to go through and do the integration by parts one more time. Hopefully just one more time. So let's change to green. So this is what we're doing the integration by parts on. Right there. I'm going to put that in brackets. It's real important that you isolate that part, the integral of x e to the x dx. And I don't include the constant, the 2 in front. Leave the 2 out in front of the brackets. So now, in this bracket, in this right here, I'm going to let u be equal to x and dv be equal to e to the x dx. And so we end up with du being equal to dx and v being equal to e to the x. And so now we put that all together in here. So what's in the green box above goes in the green box below. All right? Everything outside of the green box is the same. So in other words, all of this right here just comes down right here. So we have x times e to the x, that's my u times v, which is right here, minus the integral of v du, which is this times this, and there we have it. Now, the resulting integral, e to the x, we know how to integrate that. It's e to the x. So now here's the part where you need to be careful so that you don't get the signs incorrect. What you are doing here, let me rewrite this a little bit more clearly now. I really love to mark these things up. These are in brackets, right? So you have to distribute this -2. So -2 times x e to the x becomes this, and the -2 times the negative integral becomes +2 times the integral. So don't forget to multiply this integral by 2 and to change its sign. Now, all you have to do is integrate e to the x, which is e to the x, and you are done. So it's just like you learned in the first video. You just have to do it twice. Next up, this one looks a little longer. That's because we have to do it 3 times. So we're starting off with an algebraic and an exponential. And so the algebraic function, I'm going to color code these. We're going to do the first round in red. and that's going to be up through there. So u is 3x cubed. The derivative of that is 9x squared dx. dv is equal to e to the 3x dx, and v is equal to 1/3 e to the 3x. Then, at this point in time, I'm not going to go into the details, but you can see that all of that is put into the formula to arrive at that, and then simplify whatever you can do. And the only thing I'm doing to go to here is bringing this 3 out in front. Get the constants out. The important thing is, you can see you can't integrate this integral yet. We have x squared e to the x. Now, we started with an x cubed, and now we're down to an x squared. So that's better, but we still have an e to the 3x. So we're going to go through and do it again. Let's do it in blue now. So blue is going to take me through here. So this part just comes on down. And so remember that what is in the brackets here carries down from here. That part carries down. Everything else that's up here just comes down. And so we identify u is x squared. The derivative of x squared is 2x dx. Once again, dv is e to the 3x dx, and the antiderivative is 1/3 e to the 3x. And so just put that all into the formula to get this. Simplify anything that you can simplify, and also distribute through this -3 now, just like I did in the last problem. So distributing through that -3, this -3 times the 1/3 cancel out, and you end up with a -3 times a -2/3, which becomes a +2. So be real careful with distributing through all of the parts. So once again, let's take a look at that. You're distributing through this -3 being multiplied by 1/3, and then you're multiplying it by the -2/3. And so that's why you end up with just a -1 here and a +2 here. Well, taking a look at the resulting integral, I see we have a problem. We still cannot integrate x e to the 3x, which means I have to do integration by parts a third time. And so brackets to brackets, everything else comes down. That all just comes down. And so the third time, hopefully the third time is the charm, we let u be equal to x, du is dx, dv is e to the 3x, and once again, v is 1/3 e to the 3x. Putting all that together in the formula to get this. Simplifying it to get the next step. And then finding the antiderivatives, you end up with your final answer right here. It's a long one. Now, it's going to be very rare that you actually have to do integration by parts 3 times, but I thought I would throw one in there just so you kind of get the process down. So you're actually doing 3 problems in one here. All right. This looks like an easy one. So evaluate the integral. Yeah, we have a logarithm in here. So remember, L-I-A-T-E. We got a logarithm and an algebraic. So there's my u, there's my dv. So u is logarithm. The derivative of that is 1 over x. X to the 7th, the antiderivative is 1/8 x to the 8th. Pretty straightforward. Plug it all into the formula. Now, if these work out nicely, you're always going to be able to cancel out some of these x's. Yeah, you can x to the 8th times 1 over x just becomes x to the 7th. When that happens, that's really nice. All right, so that's easy to find the antiderivative of, and so we just end up with 1/8 x to the 8th log of x minus 1/64 x to the 8th plus c. So I want to make sure I got another one with a logarithm in there. And, oh, yeah, I remember this stuff. So we want to find the volume of a solid obtained by revolving the region bounded by the graph of f of x equals e to the negative x, the x-axis, the y-axis, and the line x equals 1 about the y-axis. So this is going back to a volume problem. Well, we know how to do those from the last chapter. So the first thing you do is go to Desmos and graph it if you want, and then make a little sketch of what that looks like here. So that's what I did. So here's my region bounded. And so remember, I always like to draw a little rectangle in there. There's my rectangles. And so I'm bounding this. I want to rotate this about the y-axis. So if I'm rotating it about the y-axis, then, and I drew my rectangles vertically, the only way to do that then would be to use cylindrical shells, right? Because that's how we do cylindrical shells. We rotate we rotate around the axis parallel to the length of the rectangle. Now you could do this by using the disk method. I'm not going to do it by the disk method, but I can show you how you might set it up. You can actually do many volume problems 2 different ways, using the disk and washer or using cylindrical shells. So remember the formula for cylindrical shells. Volume is equal to the integral from a to b of 2 pi x f of x, where x refers to the distance that the rectangle is from the axis of rotation, and f of x is the height of the rectangle. So what is it that we're actually trying to integrate then? So we're actually trying to integrate this, right? When we put that all together, the integral from 0 to 1, 2 pi x e to the negative x. Well, bringing the 2 pi, which is all a constant, out in front, we can see that what we're left with in here, we cannot integrate. We have to use integration by parts. So I identify my u as being x, my dv is e to the negative x. I get my du as dx, and v is equal to negative e to the negative x. Putting that all together into the formula right here, we have u times v minus the integral of v du. Simplifying that a little bit, all we have is double negative to get rid of to make that a plus. And so now we can integrate e to the negative x. We know we did it up there, so we don't have to do integration by parts again. Don't forget to distribute the 2 pi through everything. And so we end up with, this is my integral, but in this problem, which we haven't done in any of the other problems, is we're doing a definite integral. In all of the other problems that we've done, it's been an indefinite integral. In other words, we did not have bounds to integrate, but that's no problem. Once you find the antiderivative, once you're done, you just integrate it from, your a to b. And so that's what we're doing here, from 0 to 1. And now it's just doing the algebra. 2 pi times the quantity negative 1 over e minus 1 over e minus, in parentheses, 0 minus 1, just becomes 2 pi times negative 2 over e plus 1. This is how I left the answer. I'm not sure if that's how the answer would be left in WebAssign, but you will find that out in no time at all. All right, so that is it for integration by parts. There are only 2 videos for this. The next one, I promise, will be back to 3 videos. All right, have a good day.